Welcome to this explainer. Today we are going deep inside the belly of a modern merchant ship. We're talking up to 12,000 metric tons of steel, and we're looking at the hero and the hardware that literally keep global trade moving. It's fascinating, really, because it all comes down to the decisions made in one single room that keeps the whole shebang alive. Okay, let's dive right into this.
I want you to picture this for a second. It's 2 a.m. You're in the mid-Pacific, and the nearest piece of solid land is 900 nautical miles away. If something stops working out there, no tow truck is coming to get you. There is no spare parts store around the corner. It's an isolated, corrosive, hot, and vibrating reality where self-reliance isn't just some corporate buzzword, it is absolute survival.
And that brings us to the golden rule of the engine room. Whatever breaks, you fix it, with exactly what's on the ship, tonight. That's why understanding this machinery is absolutely critical. Before you can fix a single pipe or valve, you gotta know exactly what kind of ship you just walked onto. Because the machinery choices that naval architects made years before you even arrived, they completely dictate your daily life and your survival out at sea.
You know, a lot of folks walk onto a ship thinking marine engineer just means being a heavy diesel mechanic. No way. Actually, scratch that. You're the mechanical engineer, the electrical engineer, the refrigeration engineer, and the plumber, all rolled into one. Think of a modern ship like an isolated little town of 20 to 25 people. That town has to make its own electricity, its own drinking water, treat its own sewage, and push itself across the planet. And you? You and your tiny team of 8 to 10 people are the entire public works department keeping it all running.
All right, Section 1, meet the prime movers and rotational shaft power. Let's shift from the people to the massive hardware they actually maintain. So, what exactly does this massive machine do? Well, the prime mover is simply the machine that converts fuel energy into rotational shaft power. Why? Because at the end of the day, every ship really just has one job: make torque at the propeller reliably, non-stop, for weeks at a time. But here's the catch. There's no one-size-fits-all engine. A 300,000-ton oil tanker has totally different speed and power needs compared to a super-fast ferry. So how do engineers solve that?
Well, let's look at the engineering solutions. Section 2, 3 ways to move ships, looking at the principal arrangements out at sea today.
To really visualize this, think of it kind of like this. On one hand, you've got a single giant person turning a doorknob slowly, but with just massive, massive force. On the other hand, imagine a bunch of smaller people spinning a bicycle wheel incredibly fast, which then has to be geared way down to turn something the size of a house. That brilliantly contrasts slow-speed direct force with fast-spinning geared systems. Let's break down those 3 principal setups at a glance. First up, the slow-speed diesel. It runs at about 80 to 100 revolutions per minute, which is exactly the speed the propeller needs anyway, so it just bolts straight to the shaft. Boom. No gearbox needed. Perfect for massive cargo ships. Next is the medium-speed diesel. This one runs way faster, like 400 to 600 RPM. That is way too fast for a propeller, so it absolutely needs a reduction gearbox to slow that rotation down. You'll see these a lot on fast ferries. And finally, the steam turbine. These things are spinning at a blistering 6,000 RPM using jets of steam. They need enormous, heavy gear reductions to even be usable.
Now here's why this matters to you. The mechanical choice of that prime mover literally shapes the room you work in. If your ship has a direct-coupled slow-speed diesel, you're going to inherit a tall, narrow engine room. I mean, the engine itself can literally be 4 decks high. But if you're rocking a geared medium-speed diesel, the room is shorter and much more compact. Ship owners love that because save space equals extra cargo capacity. And if you're on a steam turbine plant, you got to make room for a massive reduction gearbox and a full boiler house to generate all that steam. Remember, this choice is locked in during the ship's design phase. You don't get to pick it. Your job is just to master whichever one you're assigned to. So why not just let the propeller spin at 600 or 6,000 RPM and call it a day? That brings us to Section 3, the propeller speed limit.
Here is a crucial rule of thumb you absolutely need to remember. 100 to 120 RPM. That is the ultimate speed limit. In order for a large vessel's propeller to operate efficiently, it has to rotate pretty slowly. If you spin it any faster than roughly 100 to 120 revolutions per minute, its efficiency just falls off a cliff. It basically just churns up the water without actually pushing the ship. And that single number is exactly why every fast-spinning engine on a big ship, whether it's medium speed or a steam turbine, literally must have a reduction gearbox to survive.
All right, quick question for you. Put on your naval architect hat for a sec. Imagine an LNG carrier, a ship hauling liquefied natural gas.
It needs to be super reliable. And historically, engineers really didn't want diesel engines anywhere near that highly pressurized, freezing cold cargo. So, out of the 3 setups we just talked about, slow-speed direct, medium-speed geared, or steam turbine, which one do you deduce was the go-to choice for decades? Think about it.
Got a guess? It was the steam turbine, and here's why. It's actually super clever. LNG cargo naturally boils off a little bit of gas during the trip. Instead of just wasting that gas or letting it become a hazard, they could pipe it directly into the ship's boilers and burn it as fuel to make steam. Plus, turbines run incredibly smoothly with very low vibration, which is exactly what you want when you're hauling massive tanks of cryogenic liquid. It just perfectly illustrates how the cargo dictates the machinery.
But as fascinating as steam turbines are, I want to leave you with this final crazy statistic. 95%. Today, roughly 95% of the entire modern merchant fleet runs on diesel. Why? How did the diesel engine so completely conquer the oceans and push almost everything else out? What makes it so dominant? Well, that staggering number is exactly why we're going to spend some serious time cracking open the ingenious mechanics of marine diesel engines in our next explainer. You won't want to miss how they solve the greatest challenges of the sea. Until then, keep questioning how the world around you works.